Okay, yeah, let's get started. If you have any questions over homework, let's reserve those for the end of class if there's time, or come to my office hours if you got questions on homework. Is the light okay like this? Y'all okay? I know y'all like it darker, but let's see how this goes. We finished up last class talking about the formula for the shortest distance between a point and a plane. And then the problem that we didn't get to do was to find the shortest distance between these two parallel planes. How do I know these planes are parallel? They're multiples of each other, but why is that? I mean, that's true, but what's the normal vector of this plane? What's its normal vector? 1, 1, 1. What's the normal vector of this plane? 2, 2, 2. So they're scalar multiples. So the normals point in the same direction, which means that the planes have to be parallel. So that's why it would work. Okay, I guess what I'm getting at is, had this been, let's say over here, a different number, well, when you said scalar multiples, like if you multiply this by 2, you don't get this, right? You would have to have a 10 out there. So that's why I wanted to clarify. It's the normal that we were looking at. Okay. All right, so the formula we had is over here in the top right-hand corner. This is in your notes. The idea was that we were going to look at a plane, and then we were going to say there's a point up here, and we were going to start by picking any point on the plane, and then creating a vector that goes from that point to our point that we want to find the shortest distance to, call that B. And then, of course, we have the normal vector coming out of the plane, which is n. So if we can figure out what B and n are, we're ready to compute the distance, shortest distance. So in this problem, we have two planes. So imagine up here that there was a blue plane up there. We need to grab a point. Those don't look parallel, sorry. We need to just pick a point on that plane. So how about a point off of plane 1? Someone give me a point up on there? How about a real nice point? Any x, y, 0 that would satisfy that equation? 0, 2, 3? That'd work, right? How about 5, 0, 0? It's even, I mean, that kills off, we don't even have x and y there. That would satisfy. So there's a point on that plane, agree? Now I need any other, sorry. Hold on, back it up. Just to make sure we're all clear. The problem is saying shortest distance between two planes. We're just picking an arbitrary point on one of the planes, right? That's our blue one, just an arbitrary point. That corresponds to, in our picture, that point right there, right? Just some point on that plane. Now, we need to pick an arbitrary point on the other plane. So what's an arbitrary point on the other plane? How about an easy one? What? 10, 0, 0. Y'all agree? That would satisfy that? So this corresponds to this point right here. So now what I need to do is generate the vector B. So the vector B for us will be what? We go from 10, 0, 0 up to the point 5, 0, 0, so negative 5, 0, 0, right? That's our B. And then what's n? It's the normal vector of which plane, or does it matter? Well, we want the bottom plane, but they're both parallel, so the normal vectors are parallel. So, but we're going to take the normal vector off of this plane. So 2, 2, 2? So all I'm going to need to be able to compute the distance, capital D, shortest distance, between these two parallel planes is take the dot product of n and b, then find that magnitude or absolute value, and then take the magnitude of n on the bottom. So capital D will be, what's their dot product? What's the dot product? negative 10 plus 0, 0, plus 0, plus 0, over now the magnitude of n. So magnitude of 2 squared plus 2 squared plus 2 squared, which is 10 over root 12, right? We could simplify that or clean it up, but that's it, right? 10 over root 12. Questions? So we only needed the equation of the first plane for what part of the problem? The only thing we needed the first equation for was to get a point, right? Once we got a point on that plane, then the question became, what's the shortest distance from that point to the other plane? All right, so that was what we had finished with last time. The next note is finding the shortest distance between a point, and this time instead of a plane, the shortest distance between an arbitrary point and some given line. So I'm going to start with a picture. Now keep in mind that in this picture, our line can be anywhere in space, right? Three-dimensional space. And our point can be anywhere. So like the point could be the projector again, and here's our line. But if we move our bodies to a certain place in three-dimensional space, it would look like that, right? So we're just going to kind of look at it from the side. So don't think we're sitting in two-dimensional space here. We're in 3D. So what I'm going to do first, to try and help you see where the formula comes for, is I'm going to imagine we have 2 points on the line. If we look at those 2 points, we can come up with a vector, A. So A, the vector A, is any vector that's parallel to our line. If we have the equation of a line, what could we use for A? If someone gives us the vector equation of a line, what could we use for A? V, right? The direction vector of the line? We could use V. But let's just stick with this right now. If we have any vector that is parallel to the line, calling it A, and we generate another vector that goes from any point on our line to the point that we're interested in, P, then the distance that we're interested in is this right here, isn't it? So we've got a right triangle here, but look, one of these sides, right, is not the length of this right here. However, check this out. If I look at this angle as being theta, right, then sine of theta would be the d that we're looking for, right, opposite over the hypotenuse, which would be the length of b. Yes, the length of b. All right, so that's where we are. That's where we are. Now, what the heck does theta have to do with anything here? Because we want to know the distance, right? So what does theta have to do with this? Well, this is a very clever thing. Taking this formula right here, multiplying both sides by the magnitude of b, we get an equation for our distance, don't we? Our distance is the magnitude of b times sine of the angle. Now right here, if you take this right here and you just multiply it by 1, but you use magnitude of a over magnitude of a as 1. So I'm introducing this hidden 1 right here, right? Why in the hell would I do that? Because magnitude of a times magnitude of b times sine of the angle between them is what? The cross product, right? This is the cross product. Now the only way that was going to happen is if I introduced that a, the magnitude of a in there. That's why we did it. So this formula reduces to this. Now notice in this formula there's no more theta, right? So all you have to do to be able to find that distance is take the magnitude of the cross product. Sorry, I said magnitude of a times magnitude of b times sine of theta is the cross product. It's the magnitude of the cross product. Okay, that's why this is the top is magnitude. And then over the magnitude of a, that's that a that we had to introduce for the 1. So this is a nice formula. All we have to do is cross 2 vectors, right? That's pretty much all the work that's required. The a here for us in the picture was any vector that lives on the line, so we could use v. And then the other vector B is just any vector going from any point on our line to the point that we're interested in. Okay? So find the shortest distance between the point 3, 6, -7 and the line that goes through two different points. So here's a picture of what's happening. I'm given a point. This is like the P. This is 3, 6, -7. And then sitting somewhere is some line. And it goes through 2 points. It's the point 0, 3, 5 and the point -4, 9, 10. So very quickly, tear out a sheet of paper. Put your name on it. This is going to be a quiz. This should take us 2 minutes, hopefully. Put your name on it. Give me, on that sheet of paper for the quiz, the vector equation of the line through those 2 points. The vector equation of the line through these 2 points. Just trying to see where we all are here, okay? And without using notes or anything like that. So just kind of fold your notes over, cover them up. See if you can remember the vector equation of a line through 2 points. I'll just give you one hint. I'm looking for R of t equals what? When you're done, turn it in. Do your own work, obviously. Of the line between 2 points. I mean, This should be trivial. This is the formula, right? We talked about this last class. R naught plus TV. That's the two things you need. Two things you need to find the vector equation of the line: a point and a direction vector, right? That's all you need. A point we get, pick either one of these points. So my R naught here would be 0, 3, 5, right? And then times T, and then V is a direction vector, which is any vector that's on the line. So the vector connecting those 2 points would be perfect, right? So just do your vector. So that's what? -4, 6, 5. Done. That's all I needed. Does that seem easy to you now? I mean, we did that last class, so all right, now you could put it together, but so that's what I was looking for. Now, getting back to this question, all we need to find the distance is a vector A, which lives on our line, which we could use this direction vector for A, right? This A. And then B is any vector that goes from here to here. Or not any vector that goes from any point on the line to the point that we're interested in. So 3 take away 0, we get 3, 6, and then what? -12. Okay. So we'll call this B. So our formula for our distance is magnitude of A cross B over magnitude of A. So we're going to need to do a cross product of those two vectors. So I'll go ahead and put them over here. Remember this way we did cross products IJK, -4, 6, 5, 3, 6, -12. Yeah. The point originally given was 3, 6, -7. Where? Right here? This should be, yeah, that should be 3. Yeah. Y'all fix that. Sorry, my mind is just up here. I'm just like, yeah, I put the wrong one. It troubles me. I mean, it really does, because I actually care about my students. Like, I want every one of you to succeed. And a lot of you want to be engineers and stuff like that. And I know what you're going to face at a university when you transfer out of here. And if you want to see hard work, wait till you see the engineers that really, really, really work. You know, the ones that are really working to be engineers. I don't want you to be shocked by that. Because if you think that this quiz was a challenge, it's not. I mean, in a class, you get homework, you're supposed to go home, you're supposed to do it, you're supposed to understand the concepts and come back to class. And when you transfer to university, you will see that. You will see that in most of your classmates, you know? Well, and then, yeah, the teacher may not really care. I'm not sure. I got an email, a text message from one of my former Cal 3 students. They're taking engineering analysis right now at UTSA, and they're begging me to come to me to get help with engineering analysis. And I'm like, I can't help you. I'm not even your teacher, and you don't even go to this college anymore. Like, you know, I want to help this person, but at some point, you have to take responsibility for your own learning. So it's only one quiz, and I'm not going to use this as the total, like, judgment of you as a class, but, you know, I don't want to have to give quizzes just to make sure everyone's, like, doing their work. I mean, this is college. You should want this. Go talk to who? Who's Rama? Where? So talk to him about. Okay. Yeah. All right. Well, so while I was up here ranting, did y'all cross product that for me? No? The whole thing is negative 87? Oh, is it? Oh, okay, you're doing. Okay. How many of you have figured out how to do it on your calculator? Okay, how many of you not done it on your, have figured out how to do it on your calculator? Why not? What are you waiting for? I said, come meet with me and I'll show you how to do it, or, stay. I mean, again, I can only take you so far here. You have to take some of this on your own. You don't want to be sitting here at the test having to do this by hand. It's just going to slow you down. You need that time. The whole thing? This right here, just the top, or the whole thing? Just top. You got 97.8? Oh, you took the magnitude already? Yeah. Okay, so what was inside the magnitude part? It was a vector, right? What was the vector you had? Negative 30. Okay, and then on the bottom we just have the magnitude of A, but A was negative 4, so negative 4 squared plus 6 squared plus 5 squared. I'll let you compute that on your own. But do you understand where all this comes from? Cross product. You have to take the magnitude still, and then you have to divide it by the magnitude of A. And then do all that, get a number. Did you get a number yet for the whole thing or no? 11.14. We're just going to take that on faith that that's correct. Conceptually, do you understand? Now, they gave you 2 points here, right? What if they would have just given you the vector equation of the line? You wouldn't have needed the points, right? You would have just gone straight to the V as your A, right? And so it would have been less work. But you still have to get the vector that goes from here to here. Okay? Which you just use R naught, right? As your point. And then the other point. All right. That's it for 10.5. Let's go 10.6. This section is really going to be a lot of you just listening and looking, not really writing anything down too much at this point. So that's why I'm gonna turn off the lights a little bit so you can really see these images. We're going to talk about what are called cylinders and quadratic surfaces. Up to this point, our three-dimensional objects that we've looked at have pretty much been restricted to lines and planes, right? Lines and planes, that's it. Now we're going to look at other surfaces in three-dimensional space, and all of them have some relationship to quadratics. In other words, are variables being squared, right? If you look at like in college algebra, y equals x squared was a parabola, right? And then you also had hyperbolas and things like that. So we had this in two-dimensional space, right? 2D. X squared plus y squared equals r squared was a circle. Notice we have two of the variables were squared, right? Two variables are squared, and then your r is a constant, isn't it? An ellipse in two-dimensional space. You had x squared over a squared plus y squared over b squared equals 1. So here what we had was two constants underneath our two variables, addition between them, variables being squared, right? That's what an ellipse was. And you change the value of a, and it changes the shape of your ellipse. And b, right? You change b, and it changes that also. So that's all. This is all review of stuff we've seen. Hyperbolas look very much like ellipses, right, in terms of the equation for them, except what? Subtraction between them. Again, you can change things here. What would happen, like right now, this hyperbola, goes like this. How can I make it go the other way, where it's on top like this and on the bottom like this? And the gap between them is in here. You don't know what I'm saying? How could I do that? What's that? Just swap this, like put the y squared right here and put the x squared right here. So right now, the negative sign is on the y, right? The y term, and the positive's on the x. If you change that, then it would go the other way. All right, so now we're going to look at cylinders and quadratic surfaces in three-dimensional space. All right, in 3D, anytime we have equations involving the three variables, x, y, z, and they don't all have to appear in the equation, all right? When we do that, we get surfaces. Before computers, the way that we graphed them was by hand, and we did these things called traces. And I can show you how to do a trace in a second, but you know, you'll see that they're quite tedious. Here's your first example of a quadratic surface, a cylinder, right? An infinite beer can, right? The traces are circles and lines. So let me go back to traces. Traces come from, if I take a 3D object, right, something 3D space, and imagine taking the XY plane, all right, and moving the XY plane up and cutting my surface with a bunch of, like a big knife that just comes through and cuts it parallel to the XY plane. When I cut through it, where I hit the object, what shape is it? And then if I come through with like the XZ plane and cut it this way, what shapes do I get? And then if I cut it with the YZ plane, what shapes do I get? And those are called the traces. So a cylinder is defined really to be a three-dimensional object where the traces that you get when you cut it are circles and lines. So let me show you with the picture. Now here's a cylinder, right? There's a cylinder. Now the equation of this cylinder, it's a spotted cylinder, sorry. X squared plus y squared equals c squared. That's the same equation as a circle, right? In two-dimensional space. But see, now we're in 3D. So the z variable, since it does not appear in the equation, is free. So what you really have is you're drawing a circle in 2D, which is the ground, right? But your z value can be anything you want, so you can move that circle up and move that circle down. When you take all the different circles, you create the cylinder. Now, if I come through and I cut it, so let me cut it with the XY plane. So XY plane is the ground. If I cut it, right, XY plane, I'm going to get what shape when I slice it? A circle, right? So here's my cut. And bring it up here. You can kind of see where it intersects, kind of hard to... Okay, you can see there with the blue, right? That's my cut. So it's circles. And as I move this thing up, I have circles the whole way, up and down. That's cutting it with the XY plane. What happens if I cut it with the XZ plane? So now it's like up, down, right? Here's the X-axis. Here's the Z-axis. If I come through and I cut through, I'm going to have, I have lines, don't I? Where it hits, I have lines. Now I have another one on the other side. That's just for my programming. When I wrote the program for this, it just made it easier to do them both at the same time. So anytime I cut it through with an XZ plane and move those planes around, everywhere I hit, they're lines, yes? And if I switch it, and I come the other way with YZ planes, it does the same thing and it creates these lines when I intersect, right? So that's what a cylinder is. It's a cylinder where you have traces that are circles and lines. The equation of a general cylinder is this. I also want to point out that since the z is the free variable, notice that our cylinder goes, you could say it kind of runs parallel to the z-axis, wouldn't you say? Now, what if I wanted to do, I'm going to come back to that one. What if I wanted to come down and have a cylinder that laid sideways and went down the y-axis instead? Well, to do that, I'm going to have, again, the equation with two of my variables squared equals a constant, so that's just like an R2 circle. But now the variable that's free is the one that I want to go down that axis. Yes? So y is free, means my cylinder will go down the y-axis. And if I wanted to go down the x-axis, the equation would be y squared plus z squared equals c squared, which is this. So the x is free. What does changing the value of c do? Just changes the radius of your cylinder, right? Okay. All right, so that's the first thing. The next thing are what are called parabolic cylinders. I mean, most of the time when we think cylinders, we think like a cylinder, like a can, but there's such thing as a parabolic cylinder where the traces are parabolas and lines. So here's your example of a parabolic cylinder. It just looks like a sheet of paper that's been folded up, right? Curled up. And the equation of this particular one is this. Z equals C times X squared. Think back to college algebra. Y equals X squared would be a parabola. If we change the number in front, that makes it more narrow or more flat as a parabola. That's the same sort of effect I have here. If I change my leading coefficient, I can flatten it out. If the leading coefficient is negative, it's going to go down, right? Back up, real narrow. You get the idea, right? So changing that C just changes up, down, or how flat. The Y variable here is free, meaning the Y doesn't appear in the equation, which gives us, again, that axis that our parabolic cylinder is going down. So if I want to switch the axis I go down, I just switch up what variables I'm using in the equation. How about the traces? We said traces are parabolas and lines. Which plane do I need to cut it with to get parabolas? XZ? Like that? If I cut it there, you can see the parabolic trace, can't you? Now, to get the lines, I cut it with the XY plane, right? I get lines. Or what about this? Let me take that other one out. Can you all see that one? It's kind of hard to see. Those don't even look right. What I could do, there they are. I'm just looking because those don't look like they hit, do they? My plane doesn't look like it hits. There's something wrong in my code, but you get the idea, right? We cut it down like this. I should hit where I hit and intersect. I should have lines. All right, so if I want to open that up, I'll come back and sketch if we have time. If Y is free, we come down this axis. If X is free, we come down this axis, right? What if Z is free? We could make it go up or down that way also. Okay, so those are parabolic cylinders. Oh, here they are, right here. See, I can make it go up and down like this, letting Z be free. I can make it go sideways like this if Y is free. Another one with Z being free. So there's lots of different variations of a parabolic cylinder, right? All right, then comes the next quadratic surface, which is called the ellipsoid. They're calling these quadratic surfaces. Why? Because in all the equations, one of your variables is squared. That's why we call them quadratic surfaces. We always have that quadratic term somewhere in the equation. So an ellipsoid looks like this. Can you all see that enough? Looks like an egg, kind of, three-dimensional. When we look at an ellipsoid, all traces are ellipses, all of them. So what I've done here, man, it's really hard to see with this projector, but do you see the red curves? I'm already showing you the traces. Instead of having to come through and cut it, they're already there. Now, right now, I'm cutting it with the XY plane. So when I cut it this way, I get ellipses. Agreed? If I cut it with the YZ plane up and down, like this, I need to switch those little red lines. And you see how they switch sideways? Like this now? So you can see those are also ellipses, especially if we turn it to the side, you can see them a little better. And if I cut it with the other plane, we have ellipses this way. So any way you cut an ellipse, you get an ellipse. Ellipsoid, you get an ellipse. Now when I say any way you cut it, you have to cut it with one of those coordinate planes or something parallel to it. Right? If I just come in here and just hack it with something else, I may not get an ellipse. Well, with an ellipsoid, I would, but with a general, like a cylinder, right? We said with a cylinder, it's either circles or lines, but if you cut a cylinder diagonally, it's not a circle, right? So these traces are created by slicing it with the coordinate planes. Okay, sketching this. Oh, an elliptic paraboloid. Did we even talk about the equation? We didn't even talk about the equation, did I? Sorry, let's go here. Let's look at the equation of ellipsoid. All variables are present. All variables are present. All of them are divided by some constant. Addition between all of them equals 1. Right? That's what an ellipsoid has to look like. Now, elliptic paraboloids. Traces are ellipses and parabolas. So here's your elliptic paraboloid. It's like a bowl, kind of. If I slice it with XY planes, I'm getting what? What are those red things here? They look like ellipses, right? Ellipses, if I look from the top. Now, if I cut it with this YZ plane, what do those look like? Yeah. I'm bringing this out a little bit the other way. The speckling isn't very good for this section, is it? You see the parabolas in here? Okay. And then the other way would be the same thing. If I cut it with the XZ plane. So we have ellipses and parabolas is an elliptic paraboloid. The equation of an elliptic paraboloid. All variables are present, right? Only 2 of them are squared. All of them are divided by a constant. But you don't have equals 1 anymore, do you? The other one, the z is on the other side, and the z is positive, isn't it? It's a positive term. All right, so the thing, z is not free in this case. Nope, z depends on x and y. If z was free, it wouldn't be in the equation at all. It's dependent.
So if you split it with, if you did like b squared over c squared and made it equal to x over a, would that change the direction of it?
Correct, yes. So the main characteristic of an elliptic paraboloid is that you have all variables present. 2 of the variables are squared, 1's not. And then you have to have the format of addition between the ones being squared and the other variables on the other side. Look, here's another one, right? This is an elliptic paraboloid. It opens out the what? Y-axis here? You could say it opens out the y-axis. And if it opens out the y-axis, notice which variable is not squared. The y. In the previous one, it opened up the z-axis. That variable z was not squared. So you see the same format in that? That one's coming out the x-axis. So the x should be on that side. Then you have hyperbolic paraboloids, where traces are hyperbolas in parabolas. This is what a hyperbolic paraboloid looks like. So it's going kind of like up in this direction, then it's going down like that. It's almost like a saddle, right? A saddle. Now this is hard to say which direction it opens, right? because it's kind of a funky looking shape anyway. Do you see, though, that cutting it with the XY plane gives you the hyperbolas? Do y'all see that? Because we have to look at it from the top. Do you see the hyperbolas? And then if we cut it with the YZ plane, those are what? God, this projector sucks. Those are what? Those red things? Parabolas, right? Parabolas. Okay, let's take a look at the equation. Ah, looks a lot like the previous one, doesn't it? But it's subtraction. So all variables are present. 2 of them are squared. 1 of them's not. You have subtraction between 2 of them. And as you might suspect, you can do all sorts of different variations. You could kind of say this opens up the y-axis, kind of, right? It kind of comes out this way. But it gets a little sketchy here, all right, when we start talking about which way the surface opens. Here's the last variation of it. Y'all getting this? Understand the equations, the relationship? All right, cones. Traces are ellipses and hyperbolas, or possibly lines. It opens in the direction of the isolated variable. So there's a cone. What if I cut it with XY plane? What do I get? Ellipses, right? Looking from the top, got ellipses that way. If I cut it with the YZ plane, I'm getting what? Hyperbolas. Now it said hyperbolas or lines, right? Do y'all see that at the 2 edges, that edge right there, it would be a line? And this edge right here. So if I cut right through the center of this, is that where I am right now? Yeah, I'm cutting right through the center of it. So if I slice it right through the center, then when it hits, it would be a straight line going through here and a straight line going through here. So, but other than that, it's going to be hyperbolas. The equation. All variables present, all variables squared. Which was very much like the ellipsoid, wasn't it? But the ellipsoid had all the terms on one side. They were all positive, right? And they were equal to 1. Now there's no more 1. It's just all variables squared, addition here, and then move the other one over, and it's positive on that side. The XY plane? Oh, yes. Yes. But you could consider that to be like an ellipse with no radius, basically. Like, you know what I'm saying? Okay. Okay, directions. Okay, so if we want our cone to open out like this, right? You would say like this opens out the y-axis. Notice where the y is in the equation. It's the one that's isolated. Yes. Correct. Not inside of it, just the surface itself. Yes, that's a good thing to point out. The equation says that if I live on this surface, I have to if the point lives there, I have to satisfy that equation. That's opening out the other way, the x-axis. Okay, we're getting down to the last few here. The hyperboloid of one sheet. Here's what a hyperboloid of one sheet looks like. To me, this looks a lot like a nuclear power plant. What do they call those things? Cooling towers? Yeah, it kind of looks like a cooling tower. If I slice it with XY planes, I get ellipses. If I slice it with YZ planes, I get what? Hyperbolas. XZ planes, hyperbolas again. Oops. What is the equation? What does that look like, the equation of? Ellipsoid, with the exception of having a negative on one of them, right? and it happens to be negative on the z, and which way does this thing open? We could say it kind of opens up the z-axis, right? Then you're saying if it was x squared here, this is all the same, just make that a minus, make that a plus, then it would go out the y-axis instead. So the one that has the negative on it is going to determine the axis that you're going to open down or be parallel to. I think the next example shows you that. Yeah, see? And this equation, right? The negative is on the y, so it goes down this way. And then if the negative is on the x, it goes down the x-axis. I believe this last one, the hyperboloid of two sheets. This is basically what happens if you take that hyperboloid of one sheet and you pinch it off in the middle and it breaks apart from itself. You get something like that. Right? Take that cooling tower and pinch it down, and then eventually it separates, and you get like a bowl on top and a bowl on top, bottom, and they're separated. Contact lenses, yeah. Notice the equation looks a lot like an ellipsoid, right? Two of them are negative, one of them is positive. And it opens up the axis, you could say it opens up the axis that the variable that's positive. Now there is a page somewhere in your book that has kind of a summary of these, but it's not as detailed as this. 10.6, let's see, it's page 578. Now, let me go back and before, I think we're at the end here. Okay. We are just some examples that we'll do, but let me show you something real quick. Do you remember that if we had this in 2D, x squared plus y squared equals 9, that would be a circle centered at the origin, radius 3, right? And then if I put like x minus 1 squared plus y plus 2 squared equals 9, the only thing I've done now is what? Shifted it, right? The center of this would be 1, negative 2, and then it would have radius 3. So what we had in probably pre-cal or somewhere maybe before that was this general formula for a circle, right? X minus h squared plus y minus k squared equals r squared, where hk is the what? The center. That's the center of a circle. So if we use this formula, we shift it, we move it, right? Well, with almost every one of these that we just did, like this cylinder, we could consider the center of this cylinder right now to be the origin. And then you could shift it by moving things around, right? Like just move this thing out the y-axis up or moving it up and down won't really change anything, right? How about this again, kind of like 0, 0 is the origin. I can move it up, down, left, right type thing. The ellipsoid definitely has a center, right? We can move that around. So let me show you with the ellipsoid how this would work. Here's a general equation of an ellipsoid right here, right? So what about if we had something like this? X minus 2 squared over 4 plus y plus 3 squared over 25 plus z squared equals 1. This would be the equation of an ellipsoid, wouldn't it? But the center would be where? 2, negative 3, 0. Right? And you can tell that by just noticing that this is the part that gives you the shift. this part, and then there's nothing here for a shift, so that's why it's 0. Make sense? Okay. That you can do for almost all the quadratic surfaces, as long as the center makes sense. So now let's go and take a look at these examples. So example 4, we'll do that one. And this is really what I would expect you to be able to do on a test or something. Reduce this into standard form of one of the surfaces discussed in this section, classify the surface, include details about the traces, direction, surface opening, etc. So I have x squared equals 2y squared plus 3z squared. What do you think? Which quadratic surface did we have that had all 3 variables present, all 3 of them squared? There's a few of them, right? But which one of them had 2 variables on one side squared and then the other one on the other side? You follow what I'm trying to get at here? You have to look back through this. Which one of these is it? How about a cone? Go back and look at cone. There we go, cone. Right, look at cone. 2 of the variables squared on one side with plus between them, the other variable squared on the other side. That's kind of what we have, right? Just generally speaking, that's what we have. But I don't have it looking like x squared over a squared or anything like that. Could I rewrite it so it looks like this? Well, maybe I'm going too fast. Is that the same thing? Yes? 2 is the same as dividing by a half. And then couldn't I look at that as being x squared over 1 squared equals y squared over the square root of 1/2 squared plus z squared over the square root of 1/3 squared? Yes? I'm trying to get it to look something like this. Oh, which variable is by itself, though? X squared? So that's not this one, right? It's not that one. It's this one, right? So this one opens out the x-axis, right? And then to actually figure out what it looks like, I'm not asking you to sketch it, I'm just asking you to classify it, all right? What is the center? What would our center of this one be if we could even talk about center? Maybe we'd say the center is where they pinch together, right? What would it be here for us? 0, 0, 0. It doesn't look like we've done any modifications to the squared parts, have we? Like that's not x minus 1. It's not y minus 2 or something like that. So this is definitely a cone. Again, I'm not sketching it, but I'm just trying to get an idea. It comes down the x-axis. If this is x, y. So it's cone, opens, down, x-axis. And one last thing, I'll say the center is 0, 0, 0. Okay? That's it. We just want to classify, get an idea what it looks like. We're not trying to sketch it. Any questions? Next one I'm going to do is example 6. So I'm skipping example 5. I'm leaving it for you. Same thing. Take that, reduce it into standard form, classify it. So we have x squared minus y squared plus z squared minus 2x plus 2y plus 4z plus 2 equals 0. So what are we going to do here? Complete the square, right? Once we complete the square, we'll start to move everything around, start to see if we can get it to look like something that we're more familiar with. So I'll have x squared minus 2x minus y squared plus 2y plus z squared plus 4z plus 2 equals 0. See, it's hard to just look at it and know what it is, right? I mean, you can't just like, oh yeah, sure, that's an ellipsoid or something like that. It's going to require a little bit of work. Completing the square on this first piece, I get x minus 1 squared. I added and subtracted 1, so I should get that. No, I added and subtracted. Take half of that, yeah. Take half of 2, negative 2, square it, add and subtract. Do I need to show that? Do I need to show that or no? Okay. X minus 1 squared, and then I subtract 1, right? What about for this one? Be careful because of that negative. You have to take that negative out first, make it y squared minus 2y, and then complete the square on what's here. So half of that, again, add and subtract 1, correct? But I'll have a negative. So that negative distributes back through, y minus 1 squared, and instead of minus 1, it'll be plus 1. And then on the last one here, this one's pretty clean. That's going to be z plus 2, and then I square it, and then I added and subtracted 4, so I'll have minus 4. Then I still have the plus 2 equals 0. And so I have, let's see, 2 x minus 1 squared minus y minus 1 squared plus z plus 2 squared equals what? 2 if I move my constants to the other side? Yes, equals 2. What does that almost look like? Was that, if that were a plus, what would this be? Before is the first quadratic surface we ever got. We didn't talk about it today. A sphere, right? X squared plus y squared plus z squared equals r squared. That would be a sphere if it was plus here, but it's not plus. We have all variables present, don't we? We have all variables squared. One of them has a minus. But notice we also have a 2 over here, right? So we can't just move this term with the negative to the right side and say, oh, we've got them all there, positive on the left, positive on the right, because of the 2. So what I'm going to do is I'm going to get rid of that 2 and I'm going to make it a 1. Why? Because I know there's some equations that have equals 1, right? So to make it equal 1, I'll divide everything by 2. Do you have an equation that has all variables squared, pluses on 2 of them, minus on 1 of them, equals 1? Hyperboloid? Hyperboloid 1 sheet, 2 sheets. 1 sheet. Hyperboloid 1 sheet. Which way does it open? To the y-axis, because the y has the negative on it. So this is a hyperboloid 1 sheet, opens down the y-axis. And what's the center? If we could talk about its center. It has been shifted, hasn't it? 1, 1, negative 2. Opposite of what we see, opposite of what we see, opposite of what we see. Okay? That's it. That's it for this section. Do you want to see how you would do traces? I'll show you briefly on an easier example than this, how you would do a trace, because I think it's a skill that you should see. Let's say I was trying to do x squared plus y squared equals, well, let's do a let's do the cylinder. That has a free variable though. We'll do the cone. Okay? We'll do the cone. That's a cone? Or I'm sorry, hyperboloid is what I meant to say. Hyperboloid one sheet. That's basically like what we just did a second ago. Hyperboloid one sheet, it's going to open down the z-axis. So it's going to look something like this. So how would I do this? Well, first, let's cut it with the xy plane. Okay, so if I'm cutting it with the xy plane, what am I really doing? What's the xy plane? When we first defined xy plane, we said the xy plane was z equals 0, didn't we? So the xy plane really means we held z as a constant, z equals 0. So if I let z be 0 here in this equation, what do I get? X squared plus y squared equals 1, right? Which is what in two-dimensional space? It's a circle, radius 1. So if I were to be trying to draw traces here, three-dimensional space, I'm trying to draw a circle on the ground here of radius 1. Now why is it on the ground? Because it's the xy plane, right? Now what I'm going to do is I'm going to take that xy plane, I'm going to move it up a little bit and slice through again. So this time let me use the xy plane but move it up. So how about moving it up 2 units? If I move it up 2 units, then I'm really cutting it with what? Z equals 2 instead of 0, right? So now rewrite the equation replacing z with 2. And what do you get? X squared plus y squared minus 4 equals 1, which is x squared plus y squared equals 5, which is a circle, radius, square root of 5, right? Which is bigger than 1. So if I move up 2 units, I'm going to draw a circle with a little bit bigger radius. You see how that works? So I would come up here and I would draw a trace up here. Notice I moved it up 2 units, right? And now I do it again. I move up again. I let z be 4, z be 10, whatever I want. And what happens as I start going up? What's happening here? It's just getting bigger radius. So what we eventually do is say, why don't I let z be just some constant that I don't know? If I do that and I rewrite the equation, I get this, don't I? If I move the constant to the other side, I get x squared plus y squared equals c squared plus 1. When c was 0, what was our radius? 1. When c was 2, what was our radius? Square root of 5. Right? You see how this would work? From this, what you're supposed to see is that as c gets bigger, your radius gets bigger. So it's going bigger as you go. Now, what if you let c be negative numbers and you go down instead? Does it have any effect? No, because it's squared, so it's going to do the same thing as you go negative. So that's why we can conclude that we're getting bigger and bigger and bigger, and then this way, bigger, 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 bigger. You see how traces kind of suck because you got to do a lot of work to get these things, right? That's only cutting it with XY plane. So if you wanted a better visual of what's happening, now what you would do is you would cut it with YZ plane, which is x is 0. Then you let x be 1, then you let x be -1, then x is 2, and then x is a constant, and you see what does that look like. Do you understand kind of the idea with traces? Another way to approach the trace idea is instead of trying to draw it in 3D, draw it in 2D. So since we're cutting with the XY plane, we're looking straight down. And what we would get if we looked straight down, we first got that radius, circle radius 1. Then as we came up, it was bigger and then bigger. And that's almost kind of like a contour map, if you've ever seen a contour map. It's showing you, the progression as things go up, the lines, the rings. And so you could label each of these, like, this is what happens when C is 0. The next one's what happens when C is 2. The next one is what happens when C is 5, something like that. And you get the idea from there. So here's my cooling tower, right? I'm not going to ask you to graph things with traces, because you could always go to Wolfram alpha. Although Wolfram alpha has had some limitations, if I do x squared plus y squared minus z squared equals 1, let's see what it does. Sometimes Wolfram alpha does not like to do things in 3D. Although it looks like it's trying. How about plot? One-sheeted hyperboloid. There we go. Oh, but you can't rotate it. In Mathematica, I can. That was the one thing about Wolfram alpha I didn't like, is their 3D stuff, you can't turn it. You know what I'm saying? Like here I can turn it. I could just shift it left and right. I can actually zoom in. You can't do that in Wolfram alpha. All right, we're done with this section. Any questions? The homework for this, I believe, is correct, but the page number is wrong. Let me see if I corrected it on here. Oh yeah, that's right. 579, 21 through 27. For these problems, just do what I did right here at the end of class. It's just figure out what it is. Tell me, which way it opens, and center if you can, and you don't need to draw it out. But, feel free to get on Wolfram alpha and type it in and see, just to verify, so you're kind of getting comfortable with what these things look like. Now, on the quiz that I gave you, right? I know you needed one. On number 3, anyone else? On number 3, it says, find the shortest distance. That's what we started class with today. Find the shortest distance from the center of the quadratic surface, 9x squared plus 54x plus 4y squared. So I give you a quadratic surface, right? You're trying to find the shortest distance from the center of that, which means you have to find its center, right? To the line of intersection of two planes. So you're trying to find the distance between a point and a line, which is the second thing we did today. The shortest distance between a point and a line. Question is, what is that point and what is the line? You have to work for that here. You have to work to get those things. So you can do number 3 now. (10-7). We have about half an hour. Y'all okay? Hanging in? All right. So vector functions and space curves. Up to this point, we have talked about one vector function. That's the vector function that I gave you the quiz on. The vector function, the vector equation of a line, R of t equals R naught plus TV. That is the vector equation of a line. Now we're going to look at, just generally speaking, vector functions and space curves. So let's draw things in 3D other than lines. A vector function, R of t equals f of t, g of t, or in three-dimensional space, f of t, g of t, h of t, where t is a real number, so t is our variable. F, g, and h are real valued functions. is called a vector function or a vector valued function. You have seen this. That's what I was just saying. R of t equals 3 plus t negative 2 minus 3t 4t. Everyone should be able to look at this right now and tell me that that draws a line, because it's actually 3 negative 2 0 plus t times 1 negative 3 4. This is our R naught. This is our V. That's our direction vector, right? That's our R naught. That's our position, our original position. This draws a line. Yes? You can kind of also tell because each one of these things are linear, aren't they? They're linear in t, so it's going to draw a line. What we're trying to see right now is that this really is a vector function where you have three functions, right? You have an f function, which is your x component, a g function, which is your y component, and an h function. If all of them are linear, you draw a line. But what if they aren't all linear? Well, you don't draw lines anymore. Okay? You draw space curves. The domain of a vector function are real numbers. That's the domain is what you plug in, right? What comes out of a vector valued function is a vector. It's either two-dimensional or three-dimensional. So vector functions go a number in and spits vectors out. Given a vector function r of t, where you have f and g if it's two-dimensional, or fg and h if it's three-dimensional, those functions are called the component functions. That makes sense that they would call them the component functions? They are the functions that represent each component. The graph of a vector function in two- or three-dimensional space is a curve in two- or three-dimensional space. Now, we are considering lines to be curves. But so a curve is general. It includes lines. As t takes on different values, the function generates vectors in the space. The graph of all these vectors is a curve, not a surface. That's key here. It is impossible to draw a surface like a cylinder with a vector valued function. Well, with the vector function that looks like this. We will actually draw cylinders with vector functions in chapter 13, but not yet. Okay? If your vector function only has one variable coming in, t, you cannot draw a surface. You can only draw a curve. So here's an example. This is a two-dimensional vector function, r of t. It has two component functions, t squared and 1 minus t cubed. These are not linear, which means our graph is nonlinear. As I let time go by, right, as t goes, for every value of t, I have a vector, don't I? It spits out a vector. T is 0, and then as it spits out the vectors, if I look at all the tips of those vectors, it creates the curve. Yes? I'll back this up just a minute. So if t is 1, plug in 1 here, right? 1 squared is 1. 1 minus 1, you get 1, 0. Does it make sense that the vector that came out was 1, 0? Which is actually I, isn't it? I hat. Also notice that for this particular function, I said the domain is t is greater than or equal to 0, which means that we were restricting ourselves in not including negative time or negative t. That's just the choice of the way it was defined. Okay, let's look at this one. Now, before we do it and look at the graph, let's talk about a few things. Is it two or three-dimensional? Three-dimensional, because it says R3, right? But you could tell because of the three components, right? Now, if we were just doing the first two components, what would you draw if you had cosine t, sine t, and that's it? What does cosine t, sine t draw as I change t? Does that look familiar? A circle, right? That's actually the way that we represented the unit circle, wasn't it? If you go back to the unit circle, if somebody were to give me an angle, which I will call t, then the x and y coordinates would be cosine t, sine t, wouldn't they? So if I change t, it starts drawing all the points along the unit circle. You following me? So these first two component functions together should draw a circle as t is varied, right, from 0 on. But what about the z component? T over 5. What type of function is that? It's linear, right? So what's happening is, as I start to draw this circle in three-dimensional space, I start to try and draw a unit circle on the ground, don't I? But my z-coordinate is getting bigger. As t gets bigger, the z gets bigger, doesn't it? So instead of drawing a circle on the ground, I'm actually going to draw like a spiral. But it's going to be a fixed radius. So it's going to look more like a spring. Do you all see that ahead of time? Now if I play it, here it is. Now time is going by. I'm drawing it, but my z component is coming up, right, as I draw. It takes me, what, 2 pi to go around once? Looking at it from directly up top, well, I can't do directly up top, but it looks like it would look almost like I'm looking at a cylinder, right, if all I saw was the edge. But it's not a cylinder because we can't draw surfaces, but it's almost like coil, right? All those points do lie in that cylinder, correct. We're going to do a problem later where we calculate the amount of work done by a person who walks up a set, like a set of stairs that go around some sort of silo like this, and we're going to compute the total work to get to the top. But we need to first understand what that path looks like. All right, so there's the path. It's represented by this particular vector function. Question? Yeah? All right, now that we have the basic idea of what a function is, a vector function, we can talk about the limit of a vector function. Just like in Calculus 1, right? We had functions and we took the limits of the functions. So we're bringing the limit back. Okay, the limit is back. Y'all love the limits, right? If you take the limit of a vector function, the good news is that all you have to do is take the limit of each of the component functions. So if you want to know what's happening to a function as t is getting close to something for a vector function, you just go look at each component and apply Calculus 1 to it. In 3D, it's the same thing. Limit goes to all three. For example, this one. Given the vector function r of t is the vector function cosine t, sine t over t, e to the t minus 1 over t, find the limit as t goes to 0. So r of t equals cosine t, sine t over t, e to the t minus 1 over t. Is that what it was? Find the limit as t goes to 0 of r of t. So what I'm going to do is I'm going to take the limit on each of these, right? Individually. So I need to find the limit as t goes to 0 of cosine t. Let's do that one first. Is there even a problem plugging 0 in, doing just like a direct substitution? Let t be 0, what do we get? Cosine of 0 is 1, right? So the first component function is a non-issue, right? It's just a direct limit, direct substitution into a function, we get 1. Everything's good? Okay, next one. Limit t goes to 0, sine t over t. Try direct substitution. You get sine of 0, which is 0 over 0, which is undefined, so that's no good, right? See, we cannot plug 0 in, can we? Right? If I just come up here and say, hey, what's r of 0? You can't do it, right? It's undefined. But our curve is headed to some value, and that's what we're trying to figure out. Where is it headed? When I say some value, I'm saying it's headed towards some, not value. What comes out of a vector function? A vector, right? So it's headed towards some vector. What vector is it headed towards? Right now, I know that the x component of the vector it's headed towards is going to 1. What's the y component of the vector headed towards? So how do we handle this limit if we get 0 over 0? What's that? It's 1? It's 1? You probably just remember that as one of the ones you really had to know. Okay, I gave a quiz on that in my Cal 1 class on Monday, and I had 2 people get it right. It was kind of like that quiz I gave you all a little while ago, where it was like I told them the day before they had to know this, and then they came in and they didn't know it. But that's 1, right? Now, what if you didn't know that was 1? What's another thing? I think I heard someone say it. Yeah, L'Hopital, right? L'Hopital rule? L'Hopital's rule? Squeeze would be too much work, but you could do it that way, yeah. L'Hopital, if you have not seen L'Hopital's rule, it's spelt like hospital, but it's L'Hopital. How many of you have not seen it, or you don't remember that? No. Okay, this take-home is going to be very difficult without L'Hopital's rule. It'll be very tough. So you need to make sure that you come talk to me or talk to whoever about how to apply L'Hopital's rule. In fact, there's an entire section in the book on what are called indeterminate forms, which I believe is 4.8. Let me verify. That if you're stuck on number 4 on the homework or on the take-home, it's not 4.8. I suggest you go back and look at this section. Where is it? Okay, it's section 3.7. 3.7 in the book. Okay, so I'm going to apply L'Hopital's rule just because, in case you haven't seen it. The way we do it is some books put an H here. How many of you saw like an H for L'Hopital's rule? Or an L? I always put L. I don't know why. I've just always done that. And how does L'Hopital work? What do? Take the derivative of the top and bottom separately. So derivative of sine of t is cosine t. Derivative of t is 1 with respect to t, right, is 1. And now take the limit again. And you just get cosine of 0 is 1, right? So that's headed towards 1. And then lastly, limit t goes to 0, e to the t minus 1 over t. So as t goes to 0 here, what's e to the 0? 1 minus 1. 0 over 0 is a bad thing, right? So L'Hopital, right? Do it again. So come in here. Derivative of e to the t minus 1 is what? E to the t, right? Derivative of e to the t is itself. Derivative of negative 1 is 0. Now derivative of bottom, 1. Now let t become 0 again. E to the 0 is 1. 1 divided by 1 is 1. So we get our limit. The limit is the vector 1, 1, 1. It's headed towards the vector 1, 1, 1. Now at 0, it's undefined, but the vectors on the curve getting closer to that are getting closer to the vector 1, 1, 1. Continuity. Given a vector, what did it mean for continuity in Cal 1? What did continuous mean? Yeah, very good. That was the definition of it. To say that a function f was continuous at some value x equals a meant that the limit as x approached a of the function was equal to the function's value at a. That's what continuity at a point meant in Calculus 1, which was a long time ago. But just if you're trying to explain it to someone that doesn't understand all that, you say basically that when you draw it, you can draw it without picking up your pencil. There's no breaks, there's no gaps, there's no holes, there's no jumps, right? That's basically the idea of continuity. Well, for a vector-valued function, it's kind of a little different, all right? We still have the same definition, all right? Continuous means that the limit of the vector-valued function is equal to the function's value at a. That means this vector here has to be equal to this vector here, which means you have to be defined at the point you're headed towards. So would this be continuous at 0? No, because it's not even defined at 0. All right, describe this curve. Quickly, what does that draw? A line. Okay, we're not. That's all I wanted to make sure. Kind of gave that away earlier, but you see that's just a line, right? Can you tell me what the direction of that line is? The direction of the line. As a vector, what is it? -1, 4, -6, right? Can you give me a point that line passes through? 1, 2, 0. Can you give me another point it passes through? 0, 0, 6, -6. What did you do to do that? Plugged in 1 for t. There you go. That's what if you want to find another point on this line, just plug in a value for t. Right? You want to find another one, plug another value for t. Find the vector function of the line segment from this to this. Now, for the line segment, do you remember the only difference between just getting the general equation of the line and just the line segment? There was one thing I said you had to do. Yeah, constrain that domain, right? Between where and where? Kinda. What were the points? Give me the points real quick. 359, -5, -7, -3. 7. Okay, we have 2 points here, right? I want to define the segment that goes between one to the other. So the way we did this, R of t equals R naught, which we'll use 359, plus t times the direction vector. What's my direction vector? And I want to go from here to here. -8 to -12, right? That will draw the entire line, right? To draw the segment, all I need to do is restrict t between 0 and 1. We did do that a while back. I said we would see it again. But this is a vector function, isn't it? It's a vector function. It draws a line. If we restrict its domain between 0 and 1, we draw just the segment between those 2 points. Is this going to be our last one? Yeah. We have about 9-10 minutes. Here's a nice application. Find the vector function and its domain representing the intersection of these cylinders. X squared plus y squared is 9. Y squared plus z squared is 4. So let me show you first what's happening here. Would you mind hitting the lights over there? That's good. We have 2 cylinders, right? Here we go, 2 cylinders. One of them has a radius 3, the other one has a radius 2. Agreed? This first cylinder opens up parallel to the z-axis because z is free, z is missing. This one opens up parallel to the x-axis because the x is missing, right? So here's my picture. Now my x-axis comes out this way, so I'll just spin it around. So there, okay? Smaller one down the x-axis, the bigger one, the z-axis. We want to find the vector equation of the curve that represents the intersection of these 2 cylinders. So what we want is this. Do you see that blue curve right there? If I pull the surfaces out completely, all right, we're looking for these 2 curves. I want to find the function that draws those 2. Why? Well, because maybe later on, I would like to know how long those curves are. Why? Because maybe I have to make 1,000,000 units of something where I have to weld along this curve, and I need to know how much welding material I'm going to need. Because I'm a company, I want to minimize costs. I don't know, but this is a weird-looking curve, right? And it's something I might need to know the length of later. Okay. So how the hell do we do that, right? They're not circles, right? If you look at them from one side, they look like circles, but they've got this kind of curve to them. Yeah? So this is actually going to be a little bit easier than you might think, all right, for this particular thing, for this particular object. So let me write down the equations. X squared plus y squared equals 9. That's one of them, right? The other one's y squared plus z squared equals 4. We okay with that? All right. Now, how can I draw a circle with the vector function? How do I draw a circle? We did it just a second ago with that spiral. How do I draw a circle with the vector function? Cosine and sine, right? That's what I used. If I did cosine t, sine t, it drew the unit circle, didn't it? And then I just changed the z-coordinate to move it up and down. Agreed? So why don't I make my vector function? Now I can't use cosine t, sine t exactly because that'll draw me a unit circle. I don't want to draw a unit circle. I want to draw a circle with radius 3, right? I want to draw a circle radius 3. I'll worry about this in a second, but do you agree that this right here would draw me a circle radius 3? And it would draw it in the xy plane. Now my z-coordinate is not a circle. Like, in other words, when I'm back here, looking at it this direction, I have a circle, right? But this is changing, right? This is going back and forth like this. Yes? Wait, did I copy the problem down right? Oh, crap. It was x plus y squared, right? X plus y squared equals 9. And then y squared plus z squared. All right, that's right. Making sure my picture matches. Goes down the x-axis. This is right. So this right here, the way it's written, would satisfy this first equation, wouldn't it? Think about it. If this is x and this is y, what's x squared plus y squared? Well, it's 3 squared times cosine squared. So that's 9 cosine squared t plus, now square the y, it's 9 sine squared t. You could factor 9 out. Cosine squared t plus sine squared t would be 1. You get 9 equals 9. That would be a true equation. So this right here would satisfy this. But the z needs to satisfy this equation, right? So what I can do is I can come over here and I can solve this for z by just isolating z and now taking the square root. Now I will have plus or minus because I'm taking a square root. So I know what my z coordinate needs to be, right? It needs to be this plus or minus the square root of 4 minus y squared. But what's y? It's 3 sine t, isn't it? So this would become plus or minus the square root of 4 minus 3 sine t squared, which is 9 sine squared t. If I close this off, this is my vector function that draws that intersection. I draw the circle that satisfies the first equation, and then I use the other one to control my z-coordinate, and then use what I know about y to come in here and replace that. Is everything in terms of t? Are all the component functions in terms of t? Yes. The other thing you have to do here is figure out what the domain is. And I have 3 minutes so I can find the domain. I can do that in 3 minutes. Is there a domain restriction on cosine? No. Sine? Over here? I just got to make sure that what? 4 minus 9 sine squared t has to be greater than or equal to 0. Agreed? Which means that 4 must be greater than or equal to 9 sine squared t, which means that 4/9 must be greater than or equal to sine squared t. And then 2/3, but you have to be careful with inequalities. You can't just take the square root on both sides. You have to do a little bit more work than that. You have to actually convert it to an equation first, solve it, and then check test intervals and stuff. I'm not going to go through all that work. I'm just going to show you what the domain restrictions would be because we're out of time. But let's go back to this. Why do I have two curves? Well, I had plus or minus, right? One of these is the plus, one of them is the minus. Okay, the domain restriction, here's the actual curves. This is what happens if I let t be between negative 41.8 degrees and 41.8 degrees. I draw these two right here. So one of them is drawing the top, the other one is drawing the bottom of this one. And then if I let the domain restriction be this one here, you get that. So for bonus, because I'm out of time, I would like for you to find the domain restriction of this function. I mean, the answers are there, but you need to show it's actually pre-cal stuff that gets you the domain restrictions. So you're trying to basically solve this inequality. Turn it in next class, beginning of class, I'll count it as bonus. All right? Now let's see if you can handle the take-home. Pretty sure you can do 5 now. Theoretically, you can do 5. You've seen it. Number 5 says, find the vector function which represents the intersection of the cylinder and the plane. Right? So you have a cylinder, and you have a plane that cuts through it. It's probably going to intersect like that, some sort of ellipse. Cuts through, right? Find the vector function that represents that intersection. That's the first thing. Now, use that vector function to determine the equation of the tangent of the line tangent to the vector at the, you can't do that yet. Ah, damn it. Okay. Well, you can't do 5 yet. All you can do is the first part. Okay, so for number 5, I'm modifying the question. Just find the vector function which represents the intersection. We haven't talked about tangent vectors yet. That's what we'll have to do next time. No, well, oh, you're supposed to do 4 of these 5. You do 3, you do 4 of these 5, but if you do number 5, you only have to find the intersection. The vector function. Where it says now use that, you don't have to do that part. Yep. All right, everyone. Have a good day. Have a good weekend, right? Yeah.